Let's talk about what you're going to learn in this class. I'm a regular listener of the Not So Standard Deviations podcast. It's a great podcast that talks about how to do data science at scale in the real world. One thing I learned on the podcast is that scientists sometimes don't get their data from a nice, clean database. That was a real revelation to me. Sometimes people get their data from really dirty text files that don't necessarily conform to the format data should be in when you need to analyze it. I also found out that there is a large number of people working with data that have zero SQL skills. That literally makes no sense to me. Even if your data originally came in a dirty flat file, you should still want to clean it up and put it in a database somewhere. It really is the easiest and quickest way to store and retrieve data. In order to do that, you're going to need to learn some SQL. SQL is a simple yet powerful language, but you don't need to know everything about SQL to use it. Most database vendors take basic SQL and add stuff to it for their particular database software. We're not going to go that deep. We're going to focus on what's called ANSI SQL. That's ANSI. Don't know what it stands for. Doesn't matter. The main thing is that's the word for the SQL standard that at a minimum every database vendor needs to comply with. And we're not even going to go over the entire standard either. We're just going to focus on those things that you need to know to pull data out of a database so you can work with it in R or Python. It depends on the size of your organization, but in all likelihood, you won't be doing data science in isolation. You won't even be doing data science working solely within your data science team. There are a bunch of different professions you'll be working with to deliver data solutions. Learning SQL will help you better integrate with that workflow. Moving data through an organization can be really simple or really complex. On the complex end of the spectrum, there could be various different database technologies involved. There could be streaming systems, batch systems, modeling, predictive, and feedback systems. You could be tasked with creating predictive models that run overnight against historical data and feed those results to a transactional system. You could work further upstream creating recommender systems. No matter where you work in the pipeline, you're probably going to need SQL at some point. This is an example workflow. This is actually the workflow I use in my day-to-day because I usually work as a one-man army. It's really simple and not at all reflective of what might be found in a larger organization. In general, what is happening is data sources are on the left, data delivery systems are on the right. In the middle is all the spindle, fold, mutilate necessary to clean and conform the data for the necessary analysis. I've got it broken out between clean data and messy data. Clean data usually comes from a database of some sort, where there is already a structure laid over the data. If it's from a relational database, it could be highly structured. Even if it comes from a NoSQL database, it will still have some sort of structure to it, even if that structure isn't permanent. Messy data has no structure. Mostly this involves free-form text. Since I know SQL, I can create this entire pipeline. This course assumes that you'll be working further to the right, nearer the delivery end of the spectrum. How this process works is I collect data from all the sources and clean up with SQL. I then dump them in a Kimball-style data warehouse. From there, I'll create special queries called views and stored procs. These are basically data sets that I can call over and over. It's necessary to do this because queries can be hundreds of lines long, and obviously, you don't want to have to write that over and over. There is also a performance incentive. When you create a proc or a view, the database will cache the results, which makes retrieval much faster. From there, I can finally start doing some data science. I'll do my analysis and shazam! Present the results to executives. Here's an example of a more complex workflow. It's the same pattern as the simple workflow, but with far more pieces and far more automation. I know some of this looks like Chinese, so I'll explain some of the parts. Scoop, Kafka, and Flume are data ingestion software. Storm and Spark are real-time data processing systems. HDFS and Hive are storage systems. Pig is a data processing language. HiveQL is the Hive implementation of SQL. Just like regular SQL, you can use it to transform data. Hive, Solr, and HBase are data storage and retrieval systems. So from left to right, pull, process, store, present. In this scenario, there is an opportunity for a data scientist to work closer to the source of data. Spark is a distributed in-memory data processing tool. It allows you to create predictive models using large amounts of data. You can create your model by analyzing data in Hadoop and deploy it over real-time data systems. This is how a lot of the most popular websites can do things like make recommendations to users. Spark also has an implementation of SQL, which we'll take a look at in lab later. The bottom line is, if you want to work in data, you're going to need to know some SQL. It will make your life so much easier. Since this is a crash course, the class is pretty basic. I'll introduce you to databases and database theory. I'll show you how to read a database diagram so you can get the data you need without having to ask someone in IT. I'll show you some basic SQL commands. I'm going to give you enough information so if you need to do something difficult, you can combine concepts and synthesize your own complex query. I'll show you examples and give you the opportunity to apply the concepts you've learned. Finally, we'll connect to some data and do some actual data science with the data we pull from our SQL queries. You'll need some software to successfully complete this course. All of these things are freely available open source software. Databricks is an Apache Spark cloud solution. There is a free community edition, and we'll be using that for. Let's talk about how to get help with this course. So first off, a couple of useful tips. You can use the video player settings to speed up or slow down the videos. You can use the Udemy app to download videos of the course lectures. And you can make sure to use Q&A or question-answer forums, since there's lots of previous discussions already available there. If you're experiencing any platform-level issues, please email support@udemy.com. Platform-level issues include things like video playback if you have blurry video, if you have questions on maybe changing your name on your certificate, or if you have issues with payments or enrollment in the course. I don't actually control any of that. That's Udemy platform level, so you're going to need to email support@udemy.com, and they'll be happy to help you out. We cannot actually help you with that. I would recommend that a really fast way to get help, especially for really common issues, is a quick Google search or a Stack Overflow search of your error. That almost always pops up the first link, which is a solution to the problem. Then, if you still can't find your solution, you can search the question-answer forums inside the course. And you can also check out the FAQ lectures. If you still have trouble finding the solution, please submit a new question to the question and answer forums, including details on what you've tried along with a screenshot of your error or code. Please include as much detail as possible so that we can help you out. Before posting to the question and answer forums, please confirm that you're running the code as originally provided and that you have tried running our provided code without any edits to them. So please confirm that you are running the original code and write that you've confirmed that when posting to the forums. It's going to save you a lot of time from simple typos. So again, simple typos can cause errors. A simple check will guarantee that you avoid any of those types of issues. Please keep in mind for the course question and answer forums, we cannot help you with your personal data projects outside of the course material. So please, keep the question and answer forums related to the course material and questions stemming directly from the course content. All students in my courses have access to the closed Mass Street University Facebook group. It's a private group for students that you have enrolled in one of my courses. As long as you're not spamming the group with nonsense, you are free to interact with other students however you choose. You can ask questions, you can share career and job search information, you can talk about projects you may be working on. As long as the conversation is data-related, it's fair game. Be sure to read the group rules before you post for the first time. Let's talk about getting the course material. I keep all of the material for every class in GitHub. The following instructions to get the course material are generic. What you're seeing on your screen may not be exactly what you see for this particular course, and that's fine. The instructions are the same for all classes. Click the Resources button for this lecture. In the drop-down, click Link to Course Material. This link leads you to a GitHub repo. If you don't know GitHub, don't worry, there's a simple way to get the files. In the upper right-hand corner, you'll see a big green button that says Clone or Download. Click that. You'll be presented with some options. You want to click Download Zip. What happens next depends on your browser and operating system. Once you've downloaded the file, unzip the file using whatever archive software you have on your machine. If you haven't already, I would recommend putting the file on the desktop where it's easily accessible. Go ahead and open the folder. In here, you'll find most of the material needed for the course. Every now and then, I may still put files and lecture resources when necessary. Most of the time, everything you need will be in here. There are some files in here that are GitHub related that we can get rid of. You can get rid of the following files: readme.md, .getignore, and license. You are free to explore the material, but I wouldn't worry about that right now. Throughout the course, we'll be talking about the material and pulling out the files we need as we go. The exception to this is references.pdf. I'll usually place all kinds of interesting information in references.pdf. It will frequently come in the form of links to information that will allow you to expand your knowledge on a specific topic. But that's it. That's how you get the course material. We are now officially done with all the introductory material. Now let's get to the fun stuff. Let's talk about basic SQL concepts. Structured Query Language, or as we pros call it, SQL. If you're going to be working with data, SQL knowledge is an essential skill to have even in the era of big data. Big data is often stored in what's called a NoSQL database. These databases are radically different from the relational databases that we've been dealing with for the past 30 years. Since a lot of big data is unstructured, it doesn't make sense to store this data in a structured way. There are technical challenges with trying to store so much information in the same way we've done it in decades past. These new databases also needed a new way for users and developers to interact with them. This has resulted in a paradigm where these new databases frequently have specific languages to interact with them that looks absolutely nothing like SQL. That presents a problem. Obviously, your initial cadre of big data professionals comes from an existing base of people who have been working with relational databases for years. There is a vast pool of people out there who know SQL. If you're trying to gain broad adoption of new technology, the best way to do that is to leverage existing skills. As a result, there's a lot of focus on developing software that allows people to query big data with their existing SQL skills. Apache Hive is one of those pieces of software. If you get a chance to play with Hive, you'll see that HiveQL, the query language used to interact with Hive databases, bears a striking resemblance to SQL. SQL is one of the first programming languages I learned. It's also my most used programming language. It's incredibly easy to learn. Every single SQL statement starts with 3 words: select, from, and where. Select the columns that you want. From the tables that you want them. Where the data meets these filter criteria. If you understand that, then you're halfway home. When I give lectures, you'll frequently hear me use the phrase the old world and new world. The tools and techniques used to store and manage data in the pre-big data world are so vastly different from how we do things today that I can't help but think of them as coming from an entirely different era. So, when I say old world, I'm referring to relational databases, even though those database systems are still around today. In the old world, we stored data in constructs that look like the spreadsheets that we're all used to working with. These constructs are called tables. If you wanted an efficient database for a transactional system, there were very specific rules about how you had to store this data. This set of rules we called normalization. The point of normalization was to eliminate errors that arose from inserting and updating data and to eliminate duplication of data as much as possible. Data were usually modeled as a set of relationships where a record in one table would relate to a record in another table. The relationships were set up as parent-child relationships, where a parent table would hold a record, and the child table would hold one or many records that were related to the record in the parent table. To ensure that the relationships were not broken, you would set up the table with certain rules. For example, a record could not be inserted into a child table without a related record in the parent table. The relationship that I just described is called a one-to-many relationship. One record in the parent table can have 0 to many related records in the child table. That is just one kind of relationship. There are several other kinds of relationships, but the 3 most common are one-to-many, as we've been talking about, one-to-one, where a record in the parent table can have one and only one record in the child table, and many-to-many, where several records in the parent table can be related to several records in the child table. Let's talk about keys. When working with data, It's important to be able to uniquely identify records. Uniquely identifying a record becomes really important when you need to delete data or join tables. When doing database maintenance, it frequently becomes necessary to blow away one and only one record. You have to be able to tell the database that this particular record and no other record is the one you want to delete. When we get to the labs, we won't be deleting data, but we will be joining tables. So, from the perspective of an analyst, it's important that you understand how tables are joined together so you can retrieve the data that you need for your analysis if that data happens to be spread across several tables. Just like relationships, there are several kinds of keys. For this class, you only need to be familiar with two: primary keys and foreign keys. Keys are implemented as special columns that have rules on them that prevent the values in those columns from being duplicated. A key could be a single column or a combination of columns. In transactional systems, the values of keys can be arbitrary and implemented as an auto-incrementing number, or they might be meaningful like customer numbers or invoice numbers. In data warehouse systems, all the keys to tables are arbitrary. This is my personal belief, but I think that every single table should have a primary key. Out in the wild, I sometimes find tables that have been implemented without a primary key, and it always causes issues. Remember our discussion on relationships? This is where foreign keys come into play. In order to relate a record in a child table back to its parent record, you need the primary key of the parent table. When you're writing a SQL statement, this is how you join data together, as we'll see in a little bit. Let's take a look at an example of how keys are implemented. This is an entity relationship diagram, or ERD for short. It's a diagram of a database. This diagram, in particular, documents the structure of Microsoft's AdventureWorks sample data warehouse. It's not the full warehouse, it's only the fact internet sales model. It captures all the facts and dimensions surrounding online transactions. We're not going to talk about the ins and outs of dimensional modeling. All you need to know for now is that facts are where we store numbers, and dimensions carry all the textual information surrounding the numbers. So a fact would be that a transaction came to $12.30. A dimension would carry the customer information for that transaction. As you may have gathered, the rectangles on the diagram represent tables in the database. Inside the rectangles is all the information about that table, such as table name, column names, data types, indexes, and whether a column is a certain kind of key. The convention of naming tables, starting off with what they are, fact or dimension, is a convention that I use when implementing warehouses. The broken lines on the diagram indicate relationships. I used Toad Data Modeler to draw this diagram and chose the option to use the crow's feet notation, since it's what I'm most familiar with. Crow's feet gets its name from how you indicate a many relationship. If you notice, most of the lines that touch the table fact internet sales end in a circle with 3 lines. This indicates that this is a many side of a relationship. If you trace the line back, you'll see it starts with a single perpendicular line. This translated means one and only one. This indicates the 1-2 side of the relationship. So using dim customer as an example, you say dim customer as a one-to-many relationship with fact internet sales. This should make intuitive sense as one customer has many transactions. As you may have figured out, this notation is also indicating that most of the dimensions are parents of the facts, making the fact table usually a child table filled with foreign keys, as we see is the case here. Take a look at dim customer again. You can see that customer key is the primary key of the table indicated by NNPK, meaning not null primary key. Plus, there is the obvious key next to the column. Now, if you look down at fact internet sales, you can find customer key, and that it's a foreign key indicated by NNFK in the gold key. And that is how you physically implement parent-to-child relationships in a database. Let's talk about basic SQL statements. Up to this point, everything has been background information. Let's now take what we've learned so far and apply it to writing SQL statements. Over the next few slides, I'm going to show you examples of SQL statements. These statements are based on a sample Postgres database that we will be using in Lab 1. Here we see examples of 2 basic SQL statements. You'll notice neither statement has a where clause. The first statement uses the wildcard symbol to pull every column from the film database. Since there's no where clause, the statement pulls every single record from the film table. Basically, what the statement is saying is, give me every single column of every single record in the film table. The second statement pulls every film record, but it's picky about columns that we're actually pulling back. In this case, the title length and rental duration columns. These two statements do close to the same thing that the previous two statements did, except this time we're going to throw some filters on the data. In the first statement, we're only going to be pulling back films with a length greater than 90. In this case, it indicates films with a length of 90 minutes. This is why documentation is so important. You need to know the units of the values you're working with. In the second statement, we are going to further filter the data so that in addition to getting films that are 90 minutes long, we are going to take that subset of data and further filter it down to only films that are allowed to be rented for at least 3 days. SQL has the standard logic operators that you'll find in any programming language. So here are two examples of actually sorting data. Sometimes in pulling back records, it's important to understand where particular values may lie in the overall data set. You can do that with the order by clause. For instance, like we see in the first example, sometimes from just a user readability standpoint, it is good to put records in alphabetical order. You can control the ordering by modifying the order by clause with the ascending and descending indicators as noted by ASC in the first statement and DESC in the second statement. Business analytics is all about counting things. That means eventually you're going to want to do math on your dataset. SQL provides a set of functions that allow you to perform various basic mathematical and statistical operations on columns of data. Some common examples are trying to find the minimum or maximum values in columns. You can do that with the min and max function, respectively. If you want to find the average value, you will use AVG. If you want to add up values, you will use the sum function, which isn't shown here. Sometimes you just want to get a count of records, and that can be done with the count function. These functions work on whatever dataset you ask for. The examples shown here are being performed on every record in the film table. Using where clauses, you can filter the dataset down so that functions can be applied to just subsets of data and not the entire table. Now the fun starts. If you're working with relational databases, in all likelihood, you'll be analyzing data in more than one table. In the real world, you might be analyzing data from a whole bunch of tables. We'll keep it simple here and just learn how to join two tables together. There is more than one way to join a table. As a matter of fact, I didn't start out writing joins like this. In college, I was taught an entirely different technique. When I got out in the real world, I started writing joins like this shown here because, to me, it's a cleaner syntax. To join tables, you can use the join on clause. Join table on primary key of parent and foreign key in child. See the C and P? Those are called aliases. It will get annoying writing table names over and over, so to keep yourself from going crazy, you use an alias. The alias acts as a substitute in your code for the table name. To reference a column, you use standard dot notation. Thus, customer.customer_ID becomes c.customer_ID. In this case, in the first example, we're joining the customer and payment tables. Another coding quirk of mine is that I prefer to put the parent tables higher in the SQL statement, and when I join them, I put the primary key to the left of the foreign key. I tend to think in pictures, and I always visualize parent tables being above child tables. So writing SQL the way I do helps me keep things straight, especially when I have to do things like join together 15 tables in one SQL statement. There is no rule that says you have to do things that way. The first SQL statement will produce a record set of all records in the customer table that you have child records in the payment table. Notice the wildcard symbol in the select clause. This will pull back every column in both tables. In the second example, it shows use of the left outer join. In the left outer join, we are going to pull back all of the records in the parent table and the connecting records from the child table. If you ran this query, you'd see that in those places where there are no connecting records, there would be columns with values of null. Sometimes when you add stuff up, you want to be able to add stuff up within certain categories. For instance, perhaps you want to look at total sales, but only for each store or department, division, or whatever. You don't just want to see it by the entire enterprise because you need to see how the individual parts of the business are doing. This is done using the group by clause. The group by clause can be a tad hard to get a hang of. The key is, anything that you group by has to be in the select clause. You can see what I'm talking about in the second example. We're grouping by customer ID, first name, and last name. Basically, we're looking for the average amount each customer has paid. In order to do that, we have to make sure those things are also in the select clause as shown. The last thing we'll talk about is aliasing columns. In your results set, column names will print out exactly as the column is named in the database. Sometimes, for various reasons, they may not be helpful. In those cases, you can rename a column for output using the as keyword. Just create your select clause as normal, but after the proper column name, put as in whatever you want the column to be named within the confines of the SQL language. As you can see here, I'm using an underscore in place of a space because spaces aren't allowed unless you put the alias in brackets. So that's it. You survived. That was a lot of information in a very short amount of time. But I gave you enough information that you can start asking questions off whatever relational database you happen to be working with. Of course, what I gave you in no way, shape, or form covers the entire body of knowledge when it comes to SQL. Even once you have the basics mastered, you have to start learning the quirks of whichever database technology you happen to be working with. The good news is, there are plenty of free resources out there to help you along on your learning journey. You now have enough information about databases and SQL to start polling your own data. Let's play around with your newfound skills in Lab 1. Welcome to Lab 1. It's time to take your newfound skills and put them to practical use in a safe lab environment. Instead of learning on production data at work, we're going to use a freely available sample database to write queries against. First, we'll talk about how the lab activity is going to go. Before you get to the lab work, we'll do a section on setting up Postgres and making sure you can properly navigate around that environment. The lab has been designed to push your new skills. Don't worry if you don't get it right. We'll review the lab in the last section, and I'll give you the correct answers. Sure, you could skip to the end, but what fun is that? The Q in SQL stands for query. When you run a SQL statement, you're basically asking a question. SQL is a very powerful language for what it is. It has all kinds of functionalities that you can use to move and manipulate data. For the purposes of this course, however, we're going to learn to use SQL as a tool to get information for our own analysis, or analysis for decision makers. This is how Lab 1 is going to work. I'm going to ask a question. Then you're going to pause the video, pull up Postgres, and using the information you learned in Section 2, answer the question posed to you by writing a SQL statement that returns the answer we're looking for. Let's try an example. Of all the films in the database, how many languages are represented? At this point, you'd pause the video, pull up the database diagram, find the table in question, and write your query, which in this case is this. Select count star from language l.join film f on l.language underscore id equals f.language underscore id. That will return a count of the records in the language table, which represents all of the languages in the database. If you're sharp, you'll see how it wasn't good enough to just count the records in the language database. The question specifically asked for the number of languages represented in the films and inventory. The language database could hold every language of the human race, and, while it is possible, it's not very likely that there are any films done in Aramaic. By joining the language table, we've ensured that we only get language records that are actually in a film in inventory. Here's a catch. While at the Air Force Academy, I was subjected to a rather bizarre bit of pedagogy that would teach us about day and then test us on night. We were supposed to answer questions about night based on our knowledge of day. While it was super annoying at the time, in retrospect, I've come to appreciate this approach. So I'm going to subject you to the same nightmare. Don't panic. This is actually a good thing because it's very real world. If you're new to IT, you might have the impression that there is shame in Googling answers. I've been coding for 20 years and I Google stuff all the time, and there isn't a software engineer that won't tell you the same. So if you're stuck, I encourage you to use Google to find an answer. Don't just skip to the answers in the last section. Do the hard work and get used to finding answers on your own, because I'll tell you right now, Googling for an answer is a lot less embarrassing than leaning over to ask a coworker about a particular function. Let's get Postgres set up. We're going to start with installing Postgres, then we'll get familiar with the UI by installing the sample database and running a few sample queries. I don't like to waste time showing people how to install software, but the installer for Postgres has some gotchas to it, and I want to make sure you steer clear. I'll just show you what to avoid and we'll move on. Instead of giving you a link that will probably expire, the next thing to do is to just Google download Postgres. Find the installer for your operating system and download it. You want the most recent version of Postgres. Once it's downloaded, start the install process. As you click through, you can pick the options already selected for you. Here's what I want you to avoid. Do not launch Stack Builder. You'll be there for hours. Just unclick that option and hit Finish. Once you're done, you'll want to launch something called pgadmin. pgadmin is the GUI for Postgres. It's a web application, so that can be a little weird if you're used to working with databases with desktop applications. We're not going to get very deep with it. I'm just going to show you what you need to know to perform the upcoming labs. But that's okay, because pgadmin is a fairly intuitive piece of software. On the left is your server objects. On the right is your query/results window. We need to install the sample database, so let's go ahead and do that. The first thing we're going to do is expand the Servers tab, then expand your instance. Now, right-click on Databases and select Create Database. Name your database DVD Rental and click Save. You can now see the DVD Rental database in your Postgres instance. Now, right-click the database and select Restore. In the File Name field, navigate to Lab 1 in your class material folder. In there will be a tar file. Select that. Now click Restore. Now we need to drill down to where the tables are in the server hierarchy. So expand the database, expand schemas, expand public, and finally, expand tables. Now you can see all the tables in the database. You can further expand the tables to see the columns in the tables and other properties of the tables. So let's write some practice queries so you can see how that works. We need to open the Query tool. That is done by hitting the Shazam button under the Tools menu option. This will open a query window where you can write SQL statements. So let's do a simple one and look at all the actors in the database. So now, in order to run this query, I just hit F5, and you can now see all the actors in the database. I believe this is the full record set, but we can double check that. Let's write another SQL statement that counts the records in the actors table. Now, what I really want to show you here is that you can have more than one SQL statement in this file, but you don't have to run everything all at once. If you want to just execute a specific statement, all you need to do is highlight what you want to execute and hit F5. As you can see, just the second SQL statement runs, and the result jives with the record count of the first, so we're good to go. Let's do this thing. So this is how this will work. I'm going to ask you a question about the DVD rental business. This is exactly the kind of work you do in the real world as a data scientist. The questions may be more complex in the real world, but the fundamental concept is the same. Use data to develop knowledge about business operations. Just like the real world, you'll have documentation about the database you are working with. Look in your Lab 1 folder and open the ERD. You'll use this, pgadmin, Google, and your knowledge of SQL to answer these questions. I will pose a question. Then you'll pause the lecture and go to pgadmin. You'll then write a SQL statement that will give you results that answers the question. Once you're satisfied with your work, come back to the lecture and press play to advance to the next question. The answer to these questions are in your Lab 1 folder. I challenge you not to cheat yourself. We'll go over the answers in the lab review. For now, just do your best to answer the questions with the resources you have at hand. Here we go, kids. Good luck. Question 1. How many films are in inventory? Pause the video and write your SQL statement. Question 2. What does a sample output of the films table look like? So think about what is being asked. We don't want all the output, we just want some of it. Pause it and go to work. Question 3. What films are longer than 3 hours? Order the output by title in reverse alphabetical order. Pause it and come back when you're done. Question 4. What films are longer than 3 hours and have a rental duration of a week ordered by rating? Here's a hint. Pay attention to the units you're working with. Pause it. Write your query. Question 5. What are the max and min rental rates of the movies in inventory? Compared to the last one, this is pretty easy. Pause it and see what you come up with. Question 6. What is the average rental rate? Compared to question 4, this is an underhand softball. Pause it and knock it out of the park. Question 7. Find the range of dates in the payment table. Frequently in the real world, we want to see what date range a data set works with. We're basically looking for the biggest and smallest dates. Pause it and come back when you're done. Question 8. What customers made a payment in May? This is the first question where you'll have to write a join to answer it properly. Consult your ERD and determine what tables you need and how to join them. Pause it and see what you can do. Question 9. What is the average payment by customer? This question is your comprehensive final. You're going to have to pull out all the stops on this one. Use Postgres documentation. Use Google. Use Stack Overflow. Just don't tell them you need help with the class. I just want to tell you good luck. We're all counting on you. And don't call me Shirley. This is your last question. Go ahead and write your SQL statement, and we'll talk about everything in the next lecture. So how do you think you did? Like I discussed before, I designed these questions in such a way that you could not just rely on your knowledge from class to answer them. This forces you to be resourceful because at the end of the day, nobody can teach you every single thing about SQL or databases. I've been doing this for 20 years, and I use Google and Stack Overflow to get work done. So it's not really about your ability to memorize a programming language's API. It's more valuable that you develop your ability to rapidly find answers when you inevitably hit the limits of your knowledge, which can happen to anyone at any time. So let's look at the answer key and see how you did. Click the Open File button in pgadmin and navigate to your Lab 1 folder. Open the file lab1 queries.sql. Question 1 is pretty straightforward. You have to use the built-in function count. As a personal quirk, I prefer to name my calculated columns just in case I need to share that number with someone. They'll see the column name without any explanation from me about exactly what it is. The answer to question 2 is Postgres specific. SQL Server does this a little differently, but it's the same concept. We want to limit the amount of records that come flying out of the database so we don't get the entire table as a result set. Question 3 required you to write a where clause in an order by statement. The keyword DESC tells the database that you want the result set to order based on title alphabetically in descending order. If you know anything about computers, you know that characters have numeric values. It's this value that the computer uses to order things alphabetically. Normally, you don't have to think that hard about it, but if you have special characters in your data, getting a proper ordering can become an issue without some data cleansing. Question 4 is question 3 with a twist. You had to convert minutes to hours, which is straightforward enough. However, if you just divided length by 60, you might notice you got a funny answer. This is because of how SQL handles data types. 60 is an integer. If you divide an integer by an integer, you get an integer. The problem is, you're dealing in fractions of an hour, and we're not rounding, which means that the answer is actually a rational number. In order to get that number, you have to cast 60 as a float, and the easiest way to do that is to just make it a float by adding 0.0 to it. Question 5 is pretty easy. Once you find the right table, you just have to use built-in functions to get the answer. Question 6 is also easy. I just wanted to introduce the average function. Question 7 is also easy if you understand what is being asked. I kind of gave that one away in my hint for the question. Question 8 is your first join. Straightforward if you understand joins. There is a subtle nuance here. I didn't specify how I wanted you to order the data, so there was no need to tell the compiler how to do the ordering. The default ordering in Postgres is order by ascending, which is what you get when you don't specify the ordering manually. Question 9. Did you get an answer, or did you give up? It was a tough one. You might have a slightly different answer because I didn't specify what columns to output. There were 2 things you needed to know. The first was when you do a group by, all the columns that are not part of the aggregate function have to be in the group by clause. The order in which they are in the clause matters because that's the order of how they will be grouped. My personal preference is to just match whatever is in the select statement. The other thing you needed to know was that in order to get the order by clause to work, you had to include the built-in function in the order by clause. If you just output the customer ID, you get partial credit. Remember, the point of all this is to get business people the answers to their questions so they can make proper data-driven decisions. They don't understand things like customer IDs unless customer ID is actually the enterprise identifier for a customer. That said, it's rarely the case that having an ID in a report is going to be valuable without the textual descriptive information to go with it. So the part of basic training where you crawl under barbed wire while I snap live rounds over your head has now ended. The rest of these labs will be a lot more show and tell than they will be things where you have to write code, although I will present opportunities for you to do that in your spare time. Let's talk about views. The SQL statements that we're learning to write are very simple, and it's not that big of a deal to write them over and over. However, some SQL statements can be quite complex. I've written SQL statements that were several hundred lines long. Obviously, it's not practical to rewrite hundreds of lines of code every time you need them. Even saving them in a file that you pull out from time to time isn't that great of a solution. If you find that you have a particular SQL statement that you write over and over, then it may be time to do something more permanent. You have some options depending on what you're trying to do. If what you need is relatively complex and requires programming structures like if-then statements, you best bet it is a stored procedure. If you have a distinct bit of functionality that isn't covered by your server's built-in functions, like maybe you need to convert Unix timestamps to dates, your best bet here is a function. If you have a statement that doesn't require any of that and you can create your data set without using things like temporary tables, then you'll want to use a view. I just used a bunch of words that you're probably not familiar with. Since this is a crash course, a deep discussion about your various options to persist a query is beyond the scope of this course. In your career, you'll run into these phrases frequently, so there is no hurry to learn everything right now. Postgres doesn't have the concept of a stored proc, so we're going to restrict this lab to working with views. The technical explanation of a view is that it's a virtual table. I prefer to think of it as a persistent query, but the virtual table definition is handy because you can treat views like a table. Once you have your view built, you access it just like you would any other table. If none of this is making sense, don't worry. We're going to do some show and tell in the lab activity. Let's go there now. Let's go ahead and go back into PG admin if you're not already there. Open the file in your Lab 2 folder called lab2views.sql. When you open the file, the first thing you'll see is a documentation block. I consider it good practice to keep views in files that you can place in source control, just like any other software. As such, it's also good practice to document your view, because it might be really complex. The view I have created here is what I would consider fairly complex, especially considering the size of the database it is written from. As the documentation states, we are trying to take a look at all customers with their geographic information and determine how much money they have spent the entire time they have been a customer. In the real world, this would be a first step in determining something called lifetime customer value. So, as you can see, this looks like a normal SQL statement with the addition of an extra line at the start. Since we want this query to persist and be available to other queries, it has to be installed. Line 7 is how we make that happen. We're going to create a view, and we're going to call it Customers by Total Spent. It's important to remember the name, because that is how we're going to reference the view from other SQL statements. Let's take a look at some other features before we actually go ahead and install the view. The first thing you'll notice is the case statement. In my data warehouse class, I teach people that when you're doing analytics, you need to make things human readable. If we were running this query out of a data warehouse, we wouldn't have to take this step. Here, we're running this query out of a transactional database, so we have to make the adjustment to the output manually. This query uses the aggregate function sum, so we do have to use a group by clause to get the results we want. Like I mentioned in Lab 1 review, the group by is ordered in the exact same way as the select clause. Let's go ahead and install our view. That's done by simply hitting this Other Shazam button over here in the query editor or using the keyboard shortcut F5. This is why I call it the Shazam button, because Shazam and you're done. Plus, you know, that whole lightning bolt thing? And it's not that much of a leap. Anyway, assuming nothing bad happened, and it shouldn't have, you'll get a message that says the query returned successfully. You'll notice that there isn't a result set. That's because we told Postgres that we want to use this query more than once. And would you please store it somewhere where we can treat it like an actual table? The query won't actually return results until we query the view itself. Let's see what that looks like. Open a new query window by pressing the upper Shazam button. In the object browser to the left, we can actually take a look at our view by expanding the DVD rental database, then schemas, then public, and views at the bottom. And as we can see it here, customers by total spent. Go ahead and expand that, then expand columns. And you can see all the columns available in our view. You query views by treating them just like any other table. So let's write a simple select statement, but use the view in the from clause like this. And Shazam! As you can see, it returns just like it was a normal table. Scroll to the right and you can see variable of interest total revs by customer. Let's find out who our whales are. Oh, sorry. I spent some time in my early 20s working in a casino. If you're not familiar with the American idiom, it means we're looking for our ballers, our high rollers, the people making it rain. Okay, I'll stop. We're looking for the people that spend the most. We do that by simply adding an order by clause in our SQL statement. And Shazam! Looks like Eleanor Hunt is our biggest customer. So you'd immediately run this information over to the marketing department where they would proceed to carpet bomb poor Eleanor's email with all kinds of enticements to come back and rent more videos. Congratulations! You have now become solely responsible for Eleanor hitting unsubscribe on the company mailing list. Just kidding. There is plenty of blame to spread around for that, not just one boffin in the analytics department. Feel free to play around with this view. You can do anything with it, just like any other table. You can even use it to join to other tables. You can do anything as long as it is within the bounds of all the rules we laid out in section 1 and 2. So that's it for writing SQL statements directly against the database. In the next 2 labs, we're going to look at how to integrate SQL with other programming languages. Let's talk about how to do that with Python. If you know anything at all about data science, and you've read my course outline, you're probably wondering where the R lab is. You can use SQL to interact with databases in R, but that is not really the preferred way to work with data anymore. Between database connectivity in RStudio and a set of packages called the tidyverse, writing actual SQL statements isn't necessary in R at all. It used to be. When I started with R, I wrote SQL to bring data into my data frames. I had considered teaching you that method, but it turns out all of my old code doesn't even work anymore. The language itself has evolved past the need for SQL. So we're going to skip R and jump right to Python. The rest of the labs in this course will be more show and tell than they will be actual hands-on coding exercises. There are plenty of programming classes for Python and Spark on this platform, so I didn't want to spend time here teaching you an actual language. Instead, what I'm going to do is show you how you use SQL with various data science tools and technologies. These tools are the exact same tools I learned when I got started doing data science, and they will help you on your professional journey. In this lab, I'm going to show you how to pull data straight from a database and into a pandas data frame using Python. I'm also going to introduce you to something called Jupyter Lab. Doing data science in notebooks is an important skill to have. There are several notebook options, and most of them are open source. Jupyter Lab is the latest in a lineage of environments that started with IPython Notebook. In the remaining labs, you are welcome to relax and follow along, but I would encourage you to download the code and play with it. Let's take a look at Jupyter Lab. Before we talk about Jupyter Lab, we have to install a few things. In this lecture, I'll talk about what needs to be installed. Once you're done with this lecture, go ahead and do the work of the installations before you start the next lecture. Let me preface this with a disclaimer and warning. This is going to be true of all MSU classes. All of our classes assume a certain amount of technical proficiency. You should be familiar with basic computer operations. We don't mean turn it on and open a program. We mean having enough technical capability to fix it yourself when something goes wrong instead of taking it to the shop. This is things like messing with your path or installing software that may not have a nice installer. No, those actually weren't random examples. We don't have the resources to show you examples of installations of software on every single operating system. If you run into a serious issue and Google can't help you, go ahead and drop a question in the course discussion. All right, onward. The first install is Anaconda. Anaconda is basically a bunch of most used Python libraries rolled into a single executable. Just like downloading Postgres, I'm not going to give you a link that might expire. Instead, just Google Python Anaconda. Once you're there, you'll be presented with download options appropriate to your OS. It's a straightforward install, so there's no reason to walk you through that. Just make certain you get the 64-bit version. There is a second piece of software that we have to install so I can show you this example. While Python is awesome, there are some things that it's not awesome at. One of those things is graphically displaying a decision tree. In order to do that, we need to download a graphing utility called GraphViz. Again, just Google GraphViz. Once there, go to Download and find the executable appropriate for your OS. Download and install it. When you install it, make note of where the executable is being installed. Unfortunately, this software isn't sophisticated enough to add itself to your system path variable, so you'll have to do that manually. If you don't know how, just Google Add to Path Variable, and the instructions in the Google result should be appropriate for your OS. The next step is we need to install a view. Open pgadmin, if it's not already open, connect to your server and the DVD rental database, and open a query window. Load the .SQL file found in your Lab 3 folder, and hit Shazam. If it returns successful, you're done. The next thing is, we need to install some Python libraries. This is a little tricky, so follow along closely. Open something called Anaconda Prompt. In Windows, you can just search for it. We use the Anaconda prompt because it gets us into Python without having to explicitly tell the machine that we'd like to make some Python commands. Basically, it saves typing. If you get a message that says requirement already satisfied, then you're good to go. In the command line type, pip install scicopg2, then follow any on-screen instructions. The next thing you'll need is a 64-bit ODBC driver for Postgres. Remember how I made you skip a bunch of stuff on the Postgres install? This is one of the things that you didn't get installed as part of that skip, because it wasn't worth all that work to just get a single thing. Instead, we can just download a driver and call it a day. Per the usual, just Google Postgres ODBC driver and click the top result. Now we got to do a little bit of extra work here. Click the link that says Postgres Download Site. Then, pick whatever installer is appropriate for your OS. I'm a Windows user, so I'm going to grab the MSI. You can see these files are dated. Scroll to the bottom to get the most recent file. Make sure you pick the 64-bit version if you have the option. If you pick the 32-bit version, what you'll wind up with is boiling seas, the dead rising from the grave, dogs and cats living together, mass hysteria. The last thing to do is to create a data source name, or DSN. This is also something we're not going to demonstrate on screen because the instructions are OS specific. The key thing is to create a system-wide DSN. Using the Postgres ODBC driver we installed, create a DSN called DVD rental. You'll see why this is necessary later. Okay, so you got all that? I actually will make it easy and provide some links and some commands, and we'll see how that goes. If a link is broken, drop us a note, and we'll get rid of the whole bloody thing, 'cause ain't nobody got time for that. Go ahead and install everything before you start the code example lecture. Of course, this is all assuming you want to run the examples. Maybe I should have led with that. Jupyter Lab is a cool application, but we're not going to get too deep with it. I'm just going to show you how to run the examples. Jupyter Lab doesn't have a shortcut to launch it, so you have to do it via the command line. So open up whatever command line utility you use. Once it's open, change directories to Lab 3 in your class folder. Once in that folder, type Jupyter Lab. It may take a bit to start up, so pause the video if necessary. Since it has detected existing notebooks, this is where you start. Let's take a look at example 1. Example 1 is a scenario where you run a SQL statement and output the results to a flat file. There are various reasons why you do this. You may not have direct database access from Python. You may have a small amount of data, so it's just easier to kick out the file. You may want to supplement the data from the SQL pool with data from other sources. You may just not have advanced your skills enough to be able to pull data directly from a database. If you look in the folder and open the CSV using something like Notepad++ or Ultra Edit or basically anything other than Excel, you'll see that this is the data from the view that we developed, BT-dubs. Never open a CSV in Excel. Excel will do stuff to the file like add characters and whatnot that may make it unable to be imported into a Pandas data frame. So in our first example, I'm just going to show you how to pull in the file and read a few lines of its contents. We do that by importing the Pandas library and then using the read CSV and head methods. You can execute cells individually through the GUI or keyboard shortcuts. If you look in your Lab 3 folder, you'll see a PDF of a list of keyboard shortcuts. For now, we're going to be super lazy and just run everything at once. Do this by going to Run all cells. The little stars next to the cells tell you it's working. And we're done. As you can see, the head method is a lot like saying select top 4 in a SQL statement. This method is useful because sometimes you just want to take a look and see what Pandas pulled in. You see the address to column? You didn't have nans in your file, but that is how Pandas interprets empty strings. Let's take a look at example 2. We do that by simply selecting that tab at the top of the notebook. So, as you can see, this is a much more complex example. The reason is, in this example, we're actually going to do some data science. We're going to run a SQL statement against our database. We're going to pull the results into Pandas. Then we're going to walk it through the data science process, which you'll learn about it the next course in the sequence if you choose to continue on and learn data science. We're going to build a decision tree model and output a picture of that tree as well as the results of that model. At this level of training, I don't remotely expect you to understand all of this, so we're only going to hit the highlights. In the first cell after the imports is where we make our database connection. Here, you'll see that we're connecting to the DSN we set up. Then, using the read SQL method, we run the view that we installed in the lab prep. Below that cell is the process called EDA, or Exploratory Data Analysis. This is where we examine the data to determine key information about the data that will impact our model building process. We look for things like imbalances in variables, how many empty string values there are, if there are any correlations between variables. There are a ton of things you look for here, which you'll learn about in the next class of the data science sequence. The rest of this is the modeling process and outputting the results. So let's be lazy again and run the whole thing. You're free to explore all of this, but discussing it is beyond the scope of this class. What I really want you to see is the pretty picture it generated. Go to your Lab 3 folder and you'll discover an image file that wasn't there before. Open that puppy up. What you see here is a graphical representation of your analysis. This is why decision trees are cool and make great training wheel projects. The output is super easy to understand. We'd have to talk more about decision trees before you understood it, but basically, what you're looking at is a big old where clause. These are rules that you can write in a SQL statement to get the records described in the last leaf of the tree at the bottom. Let's take a look at a short path so you can see what I'm talking about. See this here? This is a terminal leaf. If we wanted the 14 records that fell in this leaf, we'd just walk up the tree and look at the split values at the top of the leaf. In this case, we'd write a SQL statement that said where is foreign is less than or equal to 0.5. That makes no sense, but we're not in the making sense business yet, so just go with it. And rental duration is less than or equal to 5.5, and rental rate is less than or equal to 1.99. Since the original leaf split on rental rate also, we can stop here. Now, how is any of this useful information? Remember the name of the view we pulled this data from? Total revs by film, right? What if we wanted to predict how much money we would make on a film based on the characteristics of that film? What you do is, and this is wildly oversimplified, what you do is create a film signature. A film signature is all the information available about films in inventory, where a single record represents a specific film and there is one and only one instance of this film in the dataset. In this case, our view was our signature. Then you'd throw that data against a decision tree. That gives you your model. When you get a new film, you create the signature record of that film and throw that against the model. The model then tells you how much you'll make with that film. Cool, huh? I thought so. Let's move on to Lab 4. Both Python and R work with data in memory. That's great while you're learning, but eventually you will hit a data set that won't fit in memory. This will probably happen during your initial data science training. There are some algorithms that, as part of the processing, explode the data set far beyond its original size. There are numerous ways to deal with this, but the best approach is to use a parallel processing solution. In this lab, we're going to simulate working with big data. We won't be using an actual big data set, but we're going to pretend it's huge for the purposes of showing you that you're not just limited to the processing power and disk space of your machine. We're going to talk about three things: Apache Spark, Databricks, and a Python package called PySpark. Apache Spark is a distributed and memory processing framework. Okay, what does that mean? Let's break it down. Distributed. A fundamental principle of big data technology is spreading the work of storage and processing out over multiple machines. A full discussion of distributed processing is beyond the scope of this course. For now, it's good enough that you understand that when you work with big data, you're going to be working with clusters of machines. In memory. For decades, the way computers worked is data would be swapped back and forth between memory and disk. Now, technology has advanced to the point where you can work with data entirely in memory. Working with data in memory is much faster than swapping it to disk. When you combine that with spreading the workload over many machines, what you wind up with is a superior data processing framework. Apache Spark is one of the most popular Apache Foundation open source projects, if not the most popular. It has tons of committers and is being actively developed. There are a lot of different ways to interact with Spark. In this course, I'm going to show you how to work with Spark using Python and the Spark SQL API. The Spark SQL API allows you to work with data frames in a way that leverages your existing SQL skills. Setting up a Spark cluster is actually quite complicated, even if you have the requisite server and networking knowledge to do so. Even if you do have this knowledge, you probably don't have the resources to purchase 3 servers to play with at your house. Even if you took the approach of using AWS or Azure, standing up a cluster is still a fairly complex process made more so by the work necessary to securely connect to your cluster in the cloud. Databricks solves all these problems for you. Databricks provides a push-button cloud solution for standing up Spark clusters. There is no special networking knowledge needed. You interact with your Spark cluster using a notebook technology similar to Jupyter Notebook. Additionally, there is a free community edition that you can use to learn with as long as your data set is only a few gigabytes large. If you want the fast, cheap, and easy way to learn Spark, Databricks is the way to do it. Spark is written in Scala. That's the native language that you use to interact with Spark. But what if you don't know Scala? Well, you're in luck. These are APIs that will allow you to write Spark jobs in other languages, including Python, so if you're already doing data science with Python, you just have to learn the API. You don't have to spend time and energy learning a whole new programming language. This lab is going to be fun because there is practically no setup required. You just have to get a Databricks account and we're done. Before we log into Databricks, let's talk about PySpark real quick. Spark is written in what is, to my mind, a really obscure programming language called Scala. So when you're programming Spark jobs, Scala is what we call a first-class citizen. In other words, you don't have to do anything special. You just have to call Spark's methods just like you would any other method. I have to admit that Scala is actually a pretty impressive language, and it should be more popular. Let's call it a cousin of Java. It runs in the Java virtual machine. When you start writing Spark jobs and you start looking at the example code and the documentation, the first thing that you'll notice is Scala is far less verbose than Java. As you can see here, the Scala examples use far less code. If you're a sadomasochist and enjoy things like functional programming, then Scala is the language for you. The problem is, Scala really is an obscure language, and you can fight me on that. I know like 1 billion people, and not one of them is a Scala engineer, and on top of which, I have never seen it in job announcements. And I read job announcements like Johnson County housewives read People magazine. Okay, so I don't really know what the housewives around here read, but I do know I read a lot of job announcements, and Scala is MIA in those things. So if you write your awesome in-memory processing framework in an obscure language, how are you going to get people to use it? The answer is, you write APIs for other languages. Spark has APIs for a handful of languages besides Python, but we're going to pretend those don't exist. Because at MSU, it's Python or get out. So PySpark is the Python API for Spark and comes in handy. So at this point, we have to rip up the script. I had originally planned to show you some PySpark, but I recently learned that Databricks has a solid SQL API for Spark. Since we at MSU are all about the new hotness, we're going to skip PySpark and just take a look at the SQL API. Go ahead and Google and pull up Databricks if you haven't already. Go to Login in the upper right-hand corner. Now you don't want the paid version. What you really want is the free Community Edition. It's limited in what you can do, but not so much that you can't give Spark a good workout, and it's fantastic for learning. So go ahead and click the link for the Community Edition. If you need to get an account, go ahead and sign up. Once you've logged in, you'll be presented with a welcome screen that holds all kinds of get started goodies. But you can bypass all that because getting started with Spark is literally as easy as 1, 2, 3. 1. Create a cluster. You do that by clicking on Cluster off to the right. In the upper left, click Create Cluster. Enter a name for your cluster, then go ahead and leave everything else at default. Now click Create Cluster up top. Wait for it. Boom! Cluster spooling up. You have to wait till the cluster state is on running before you can do anything else, but this won't take long. When that happens, you're good to go. 2. Let's create a data table. Do that by clicking Data, then click Add Data. There's a file in the Data folder of your Lab 4 folder, so navigate there and drag and drop that file onto the target area. Once it's uploaded, click Create Table with UI. Click Preview Table. Now, here's the important part. What we're doing is creating a reference to our data that the SQL API is going to treat like a table, so we don't have to have an awkward name. So give your table a simple name. While we were yakking about table names, Databricks examined the data and made a bunch of inferences about what was in the file. We're not going to mess with any of the data types, but we do need to tell the system that there are column headers. Go ahead and click First Row is Header. Then, it's going to chug for a bit. Once it's done, click Create Table. Boom, done. Now we can treat that data just like a table. 3. Create a workspace. Click Workspace. On your ID, click down arrow, Create, Notebook. Give it a name. You can be more verbose here because it's essentially a file name. And click Create. And we're done. Congratulations! You just spun up a Spark cluster. Let's start crunching data. So, as you can see, this is just like a Jupyter notebook, and the same commands and keyboard shortcuts will work here. First, let's take a look at some sample data without opening the source file. We can do that by looking at the top 10 rows. Remember how to do that? We didn't go over this in the last lab. To execute a single cell, you just hit Control and Enter simultaneously. I'm not going to bore you with the technical workings of Spark. I have a whole other class for that. In short, what happened here is Spark took your SQL, compiled it to an executable, and then ran it over the data. This isn't impressive because we're not actually playing with big data. Believe me, if you had 1 billion records, this is a lot more impressive. How many records do you have? Well, let's find out. To insert a new cell, hit B on your keyboard. Remember how to count records? Now, that took way longer than it would if it were in a database. The funny thing about distributed technology is on smaller data sets, it actually performs worse. But that's fine. This is all just fun and games. You don't need this much horsepower for a little over 1,000 records. If you really want to have fun with this, find something in the gigabyte range. The limit on the free version is 6 gig, but for a CSV, that should be quite a few records. Drop that in and see what happens. Now, I have a challenge for you. In your Lab 4 folder, there is a PDF called Lab 4 Coding Challenge. In there are a bunch of questions. See if you can answer your questions using your SQL knowledge. The SQL file holds the answers, and you can import it into Databricks just like a notebook file. Just go to Workspace, down arrow, Import, and drop your file. Try to see how many you can get before having to peek at the answers. With the limits on the Community Edition, your cluster will spin down by itself. You can safely exit, no harm, no foul. If you want to manually do it, just go to Clusters, click your cluster, and click Terminate and Confirm. Then, just as an extra cleanup, hit Delete and Confirm. You're good. You don't have to babysit it, but it won't take long to die. All right, that's all, folks. Let's wrap this up. So that's it, boys and girls. You now know just enough SQL to be dangerous. What you've learned in this course is more than enough to go to work tomorrow and start writing your own queries. I hope you've gotten what you need from this course. I also hope that you're able to take this information and significantly increase your income, the way I did when I started my database career. If you're going to invest in education, I believe you should get a return on your investment. All of my courses are designed to give you the skills necessary to demand a higher salary or consulting rate in the marketplace. I strive for excellence in all things. However, I frequently fall short of the mark. You can help me with this. This course was built from my personal experience. While that experience is vast, it doesn't encompass the entire universe of possibilities. If you feel like there is a topic that I should expand on, or perhaps an aspect of SQL that you feel I should cover, feel free to drop me a note through student support. I'll take those suggestions and, based on demand, I'll incorporate them into the class. This is the second course I've published, and I have many more planned. I look forward to seeing you in my other courses. Ta for now.